Did you know that farming uses 70% of the world's fresh water? With our global population soaring and clean water becoming scarcer every day, this isn't just a statistic, it's a ticking clock for global food security. But what if we could turn agriculture's biggest waste product into its most valuable resource? Welcome to the Fields of Innovation YouTube channel. Smart farming starts here. Discover the future of agriculture, where we share information about technology applied in agriculture. Today, we're diving deep into the world of agricultural wastewater treatment, exploring the top technologies that are helping farmers recycle water, save money, and build a more sustainable future. The global water crisis is one of the most pressing challenges of our time. Agriculture, as the largest consumer of fresh water, sits at the heart of this issue. It takes an immense amount of water to grow our food, from irrigating crops to sustaining livestock. As populations grow and climate change intensifies drought cycles, the freshwater sources we've always relied on are becoming dangerously depleted. This directly threatens food security, as water shortages lead to lower crop yields, reduced farm productivity, and disruptions in global supply chains. This is precisely why recycling agricultural wastewater is no longer an option, but a necessity. By treating and reusing water on site, farms can create a closed-loop system. Instead of allowing nutrient-rich runoff from crop fields or contaminated effluent from livestock operations to pollute our rivers and groundwater, advanced treatment technologies can convert this wastewater back into a clean, reusable resource. This single act reduces the strain on freshwater sources, protects fragile ecosystems from pollution, and creates a resilient, sustainable strategy for farms of all sizes, from small family operations to large industrial enterprises. The benefits are compelling. Reusing treated wastewater significantly lowers irrigation costs, as farmers no longer need to purchase as much fresh water. It also helps them avoid hefty fines for environmental pollution and minimizes the overall environmental footprint of their operations by capturing and treating contaminants at the source. These systems prevent nutrient leaching and limit eutrophication, the harmful algal blooms that choke aquatic life. Ultimately, embracing water recycling helps farms comply with increasingly strict environmental regulations while securing their long-term viability. To understand the treatment process, we first need to recognize that not all agricultural wastewater is the same. The sources are diverse, and each produces a unique type of effluent. Livestock farms generate manure-rich wastewater, high in organic matter and pathogens. Aquaculture systems produce water containing uneaten feed, fish waste, and ammonia. Runoff from crop fields is often loaded with fertilizers and pesticides, while modern greenhouse systems create specialized nutrient solutions that require careful management and disposal. The common culprits found in this water include nitrates and phosphates from fertilizers, which are notorious for causing algal blooms in nearby water bodies. Pesticides, used to protect crops, can pose significant toxicity risks to both wildlife and humans if they enter the water supply. Sediments from soil erosion can also wash into waterways, reducing water clarity, harming aquatic habitats, and clogging vital irrigation equipment. Treating this wastewater presents unique challenges. Unlike municipal wastewater, agricultural effluent often has a very high organic load, meaning it's packed with dense organic material that requires more intensive treatment. Furthermore, its contamination levels are highly variable, fluctuating with rainfall, seasonal crop cycles, animal feeding schedules, and day-to-day farm management practices. This inconsistency demands robust and adaptable treatment technologies. The first step in any treatment train is primary treatment, designed to remove the biggest and heaviest contaminants. Sedimentation tanks are a simple, low-cost solution where gravity does the heavy lifting. Wastewater is held in large tanks, allowing heavy solids like soil and organic debris to settle to the bottom for easy removal. This process is often preceded by screening and coarse filtration. Mechanical screens, acting like large sieves, catch and remove large debris such as straw, leaves, manure chunks, and even plastics, preventing them from clogging and damaging more sensitive downstream equipment. The primary goal here is to reduce the total solid load, which greatly improves the efficiency of the subsequent biological and advanced treatment stages. Next is secondary treatment, where biology takes center stage. This stage uses microorganisms to break down dissolved organic matter and nutrients. Aerobic and anaerobic digesters are two common approaches. Aerobic digesters pump oxygen into the wastewater, encouraging oxygen-loving bacteria to rapidly consume organic compounds. In contrast, anaerobic digesters work in an oxygen-free environment. These systems are particularly valuable as they not only treat wastewater, but also produce biogas, a mixture of methane and carbon dioxide, which can be captured and used as a renewable energy source on the farm. Constructed wetlands offer a more natural, passive approach. These engineered ecosystems mimic the purification processes of natural wetlands, using a combination of soil, aquatic plants, and microbial life to filter water and remove pollutants. They are low energy and aesthetically pleasing but require more land. For more intensive operations, biofilters and microbial bioreactors provide a compact and highly efficient solution. In these engineered systems, specialized microbial communities are cultivated to break down specific pollutants like nitrogen and phosphorus, making them ideal for treating concentrated effluent from livestock and aquaculture farms. These microbes perform critical functions, converting toxic ammonia into harmless nitrogen gas through a process called denitrification and absorbing phosphorus into their own biomass. After biological treatment, the water may still contain fine particles and dissolved chemical compounds. This is where advanced filtration technologies come in. Sand filtration is a classic method where water percolates through layers of sand and gravel, effectively capturing fine suspended particles and reducing turbidity or cloudiness. For a higher level of purification, activated carbon filtration is used. The porous structure of activated carbon is excellent at absorbing stubborn organic chemicals, pesticides, and compounds that cause unpleasant odors, making the water suitable for high-value or sensitive crops. These pressure-driven systems produce high-quality output, often serving as a crucial pre-treatment step before the most advanced membrane technologies. For the highest level of purification, farmers turn to membrane technologies. These systems use semi-permeable membranes to filter out contaminants at a microscopic level. Ultrafiltration, or UF, uses membranes with tiny pores that block bacteria, viruses, and fine colloidal particles. It's an excellent polishing step. Nanofiltration, or NF, goes a step further, with even smaller pores capable of removing dissolved salts, pesticides, and small organic molecules. It's particularly useful for softening water or reducing specific nutrient concentrations. At the top of the pyramid is reverse osmosis, or RO. This technology forces water through an extremely fine membrane under high pressure, removing nearly all dissolved salts, nutrients, and contaminants, producing water of near-pure quality. While membrane systems offer unparalleled water quality, they come with higher costs. They require significant energy to operate, regular maintenance to prevent fouling, and eventual membrane replacement. Farmers typically choose these advanced systems when absolute water purity is non-negotiable. For example, when growing sensitive crops like berries and vegetables, operating closed-loop greenhouse systems, or needing to meet extremely strict water reuse standards, even after filtration, disinfection is a critical final step to ensure the water is safe. This stage targets any remaining pathogens, like bacteria and viruses. UV treatment is a popular chemical-free method that uses ultraviolet light to damage the DNA of microbes, rendering them unable to reproduce. Ozone treatment is another powerful option, where ozone gas is injected into the water to oxidize and destroy pathogens and organic pollutants. While highly effective, it requires specialized equipment and skilled operation. Chlorination remains a cost-effective and widely used method for disinfecting large volumes of water, though careful management is needed to avoid the formation of unwanted chlorinated byproducts. Ultimately, disinfection ensures that the recycled water meets stringent safety standards, such as those set by the World Health Organization and the FAO, protecting both crops and consumers. For farms dealing with particularly stubborn contaminants, advanced oxidation processes, or AOPs, offer a powerful solution. These processes generate highly reactive hydroxyl radicals, which are among the most powerful oxidizing agents known. They can aggressively break down complex and persistent organic pollutants like pesticides, antibiotics, and other industrial chemicals that are resistant to conventional treatment methods. AOPs are therefore ideal for farms with a history of heavy pesticide use. Large animal feedlots, or greenhouse operations where complex chemical residues can accumulate in the wastewater. Tying all these technologies together is the power of IoT and smart monitoring. Modern treatment systems are increasingly equipped with sensors that provide real-time data on key water quality parameters like turbidity, pH, and nutrient load. This data is fed into a central control system, which can send automatic alerts to a farmer's smartphone if contamination levels spike or if a component of the system malfunctions. This level of automation and remote control allows for the optimization of chemical dosing, pump usage, and filter cleaning cycles, saving significant labor, energy, and costs, while ensuring the system operates at peak efficiency. Once treated, the water is ready for reuse, but it must be applied thoughtfully. International safety guidelines from organizations like the WHO and FAO define the acceptable levels of pathogens, heavy metals, and chemical residues for safe irrigation. While highly treated water is safe for all crops, water from simpler systems is often best suited for fodder crops, cereals, industrial crops like cotton, and fruit trees where the water doesn't directly contact the edible portion. Using recycled water on vegetables that are eaten raw requires the highest level of purification and disinfection. There's an added benefit. Treated wastewater often contains valuable nutrients like nitrogen and phosphorus. When used for irrigation, This nutrient-rich water can reduce the need for synthetic fertilizers. However, farmers must engage in careful nutrient management and long-term soil monitoring to prevent issues like salinity buildup or nutrient imbalances over time. A thorough cost-benefit analysis often reveals that while recycling systems require an initial investment, the long-term savings on water bills, fertilizer costs, and environmental compliance fees deliver a positive return on investment. These technologies are not just theoretical, they are being successfully implemented worldwide. Large-scale megafarms in the United States, the Middle East, and Australia are recycling millions of liters of water daily, drastically reducing their dependence on strained freshwater resources. In the Netherlands and Israel, innovative greenhouse operators have pioneered zero-discharge closed-loop systems where virtually all water and nutrients are captured and recycled, maximizing efficiency and minimizing environmental impact. These successful models demonstrate the economic and ecological benefits of water recycling, offering a proven blueprint for other regions to follow. Of course, challenges remain. The high capital and operational costs of advanced membrane systems can be a barrier for smaller farms. Furthermore, these sophisticated systems require skilled technicians for maintenance, calibration, and troubleshooting. But the future is bright, with ongoing innovations aimed at making these technologies more accessible. Researchers are developing solar-powered treatment systems to reduce energy costs, using AI to predict contamination events and automate treatment processes, and designing new low-energy filtration materials. In conclusion, wastewater recycling is absolutely essential for the future of agriculture. In a world facing increasing water scarcity, it represents a pathway to ensuring water availability, protecting our precious ecosystems, and supporting sustainable food production for generations to come. For farmers, the key takeaways are the incredible potential for improved efficiency, significant cost savings, and long-term operational resilience. For researchers and policymakers, the focus must be on making these technologies more affordable and accessible. Adopting sustainable water technologies is not just an act of environmental responsibility. It is a smart economic decision that prepares the agricultural sector for the challenges of a drier, more crowded world. Thank you for joining us on Fields of Innovation. If you found this video helpful, please give it a thumbs up, subscribe to our channel, and hit the notification bell so you don't miss our next exploration into the future of agriculture. We'll see you in the next video.